we're going to look at why things roll. We're also going to look at rotational work. We've done linear work. Now let's see how it applies to things that spin. So the first thing we're going to look at this object rolling down a ramp without slipping. And we've used this condition before, but let's identify the courses. And by courses, of course, I mean forces on this object. Gravity pulling down or towards the center of the Earth, normal force perpendicular to the ramp, and the force of friction. But now since we're considering torque, where the force is going to matter. So why does it roll? Well, normal force isn't going to exert a torque, because here's your radius vector for the normal force. Same thing for the force of gravity, because remember your radius vector is always from the center. But here, your torque, so if torque is equal to R cross F, well, the force of friction is going to put a torque, which is going to angularly accelerate the ball and cause it to roll, which is great. So now let's figure out what type of friction is it. Is it static or kinetic? Well, if we look at this piece, as it rolls, it's just going to go down, but this piece is just touching right here. That piece is stationary, it's not skidding, so it is in fact static friction. And now that we know that it's static friction, well, let's just use, wait a minute, can we do this? No, not that easy, unfortunately, because static friction is less than or equal to mu times n. Static is just a condition. We don't know if the force of friction is at its maximum value, like just before it starts to skid, or if it's, less than that. Or if the force of friction is less than that. Okay. So now we need to find a different way to do this. Well, I propose we'll just use sum of forces equals ma. And again, same way, we'll divide it up into the x and y directions. I'm going to start with y, because if I define this as y, is it accelerating up or down in the y direction? Nope. And the only forces I have to worry about are normal and the y component of gravity, which is mg cosine theta. This angle right here is theta. Well, that's useful. Now what? We had so much fun in the y direction, why not go with the x direction? And the forces we have, again, we have theta and friction. All right, so force of friction, that's what we're trying to solve for, and max. But we don't know max either. All right, okay. So how do we get it? Well, let's use the third tool in our toolbox. We'll use torque that we've just been talking about. Funny how that works. Just when we need it, it's here. So we're going to look at the sum of torques and how this object is going to angularly accelerate. We know that angular acceleration is plus or minus r alpha, so I'm going to go ahead and plug that in, substitute it in because I had ax before, so I want to relate the two. And my torque is just the force of friction times r. This plus or minus depends on how it's going to roll. All right? So if it's going to accelerate in the positive x direction, which way does it need to spin? Clockwise being negative, counterclockwise. We talked a little bit about in class. We will talk about it more. Now we have this really fun expression for the force of friction. Oh, and it's related to our linear acceleration in the x direction. Hooray! So let's go figure this out. Well, mg sine theta, because this is the x component. I've got an ax here and ax here. Oh, this looks like some algebra time. We will put them together. We're going to start combining like terms. Oh, look. Our m's went away. R squared goes away. 2ax, or I get the linear acceleration in the x direction is g over 2 sine theta. And I got this because I had to relate angular acceleration to torque. So now let's combine these to find the total force of friction. So we're just going to substitute this back in. Math time, your r's again cancel out, and your force of friction is mg sine theta over 2. So we were able to calculate the friction on this ramp, which may be less than mu n. Pretty cool. We're going to talk about the other side of this coin, work and power. So here are our linear terms, and we want to switch them to angular terms. So work, instead of forces, we're now going to use torque, forces at a distance that cause a change in angular displacement instead of linear displacement. And instead of a change in linear velocity, we're looking at a change in angular velocity. So the way it's going to work is exactly the same way we've been using it before. Let's look at the work done by friction on an object, though. So static friction on an object. Notice this point sticks here. As it rolls, now the green point is touching the ground. But that red point didn't go anywhere. So this d theta is actually 0, because the point where the ball is touching the ground isn't moving. It has a velocity because it's going to rotate around the circle, but its displacement where it makes contact with the ground is 0. And just for fun, let's look at a lawnmower. So at lawnmower, you have a cord 0.8 meters long. You're going to pull it with a force of 80 newtons, and I give you its moment of inertia for that little pull disc. It is a super fun thing to do. So let's take a look. The work, I know torque is just R, F, and we're going to assume that since it's pulling the cord this way, that this angle between your radius vector is 90 degrees. So sine 90 degrees is, of course, 1. And now all I have is this d theta that I don't know. Well, I'm going to relate it to s. S is the angular distance, and I'm going to pull it, I'm sorry, not angular distance, arc length. Now, the length I'm going to pull it is just how long that cord is. So I relate r and theta ds over r. Oh, look, those r's are actually the same. And this ds, as we mentioned, and you get the amount of work done. So that's the rotational work. What's the final speed? Well, let's look at the change in rotational kinetic energy. Because I'm looking for velocity, I want to use change in energy. Remember, if you're looking for velocities, change in. If you're looking for accelerations, you can take the derivative, which is also a change, but it's a different way of looking at it. 1/2 I omega final, and I get that the final angular velocity is 25.3 radians per second. I hope that helps. Please ask in class if you have any questions, or shoot an email to your instructor. I hope this helps. I'll see you in class.